Thank you. Alrighty. So yeah, hopefully that was pretty okay. Kind of just making sure we were staying on top of what we covered last time. Last time we talked about the slowing down process. We also talked a lot about scattering because scattering is the process by which neutrons that are usually born fast will slow down to thermal energies where they're more likely to cause a new fission. So today we're going to cover lecture 9, which is all about heterogeneous systems. Real reactors are heterogeneous systems. And so we're going to talk a little bit more about the more detailed approach that we would need to deal with real reactors versus the homogeneous kinds of reactors that we talked about up till this point. I just had a couple things that I wanted to mention, kind of picking up where we left off last time. I had two slides that I didn't get to finish last time. Last time we introduced this quantity, which looks like a squiggle. We can call him squiggle or worm or xi. Um, and that is representing the lethargy gain or yeah, representing the how did we So change in lethargy was U final minus U initial, and then this quantity that we called worm was the average lethargy gain per collision. And so that's um, yeah. So basically, like if you have a neutron that collides with something per collision, how much lethargy does it gain? Which is another way of saying how much does its energy decrease? And with that property worm, and also with the concept of lethargy, we have a couple figures of merit that we can use to characterize how good is a given moderator. In general, you want a moderator to have a high value of worm, which means that it's going to lose a lot of energy or gain a lot of lethargy every time it scatters off of something. So we want high value of worm. We also want a high scattering cross section so that it's just more likely that when our neutron collides with something, that the reaction is a scattering reaction. And then the other thing that we want in terms of like making sure that a neutron can survive and make it to cause a new fission is that we want our moderating material to have a low absorption cross section. So we want a low sigma A so that when our neutrons are colliding with the moderator, they don't get absorbed in it. Otherwise, they can't cause a new fission. And so we kind of have two important figures of merit for evaluating a moderator. One of them is the moderating power, which is worm times the scattering cross section. And the other one is the moderating ratio, which is worm times the ratio of scattering to absorption. And so if you know worm, which you can find if you know what the material is, if you know alpha, which means that you know big A, then you can calculate worm. So like if I tell you it's hydrogen, you have the equations that you could use to calculate worm. And if you know the energy that the neutron is born at, which for most neutrons is around 1 MeV, and also if you know what the final energy of the neutron is, like if it's a thermal neutron getting to the thermal range, that would be like around 0.0001 or around like 1 ev to like a tenth or like a hundredth of an ev is around the range where we would say that they're thermal. Then that would mean that you would know the initial energy, which would be like 1 mev. You would know the final energy, which would be like 1 ev or zero point 0.1 or 0.01 ev. And if you have those three things, then you can use the definition of the lethargy gain per collision, which is the 1 over worm, and the definition of the total lethargy gain to get a figure of merit, which is the number of collisions. And this basically tells you if my neutron is starting at this fission energy and is ending up at thermal energy, interacting with some moderator, on average, how many collisions would it take to go from fast to thermal? And so ideally the number of collisions would be small because then it would mean like if you had some special nuclei where in one collision it could go from 1 MeV all the way to thermal, then that would be awesome. Um, And so this is a table of common moderators and some moderating information where this is the average number of collisions, which you can write as the average of n. Um, and this is comparing it for water, for deuterium, for helium, for carbon, and then for like uranium-238. And so, depending on the moderator, you're going to have different values of the moderating power and the moderating ratio. And it's kind of a balance of both of these things that you would want to consider. Like, if you just looked at the moderating power, you might think that water is better than deuterium because its moderating power is higher. But the moderating ratio for deuterium is way better, and that's because deuterium has a very small scatter absorption. Deuterium has a low absorption cross section, which means that you get a very good neutron economy if you use D2O as a moderator, because those neutrons can very easily have scattering reactions that lower their energy and that don't result in them being absorbed. So that was all that I want. That kind of concludes everything we needed to know about chapter 4. And then now we're getting into chapter 5 in terms of the Svetkov notes. And so at this point, we've been dealing with lots of homogeneous systems where, like, within any given region, it was all one material. And in a real reactor, you have lots of different materials that are involved in like designing a reactor core. And so real reactor cores are really heterogeneous systems in the way that you have to analyze them. And so the reason that we have these reactors set up this way is because nuclear reactors are trying to achieve a lot of things. You're trying to make sure that your reactor is critical. You're trying to optimize, like if you put fuel in a reactor, how long can the fuel stay in the reactor before you have to move it? That also is kind of related to the enrichment of the fuel that you use, because generally, if you have higher enrichment, that means that your fuel can be critical for longer. You also want to make sure that you don't melt your reactor down. So you have lots of thermal considerations in terms of like, what kind of coolant do I use to make sure that things don't get too hot? Um, there's lots of these are big complex mechanical systems, and you want to make sure that your reactor like doesn't tip over, that the fuel that's in your reactor stays where it's supposed to. So you have lots of concerns about like the structural integrity and how you are keeping your fuel and how you might be moving your fuel around. And then if you need to shut your reactor down, then you want to have ways that you can make your chain reaction stop, which is what our control rods are for. We also use things like insertable poisons in some of our reactor designs. A poison meaning like a neutron poison, not like a human poison. And so that is a way to kind of in a way adjust the criticality of your reactor such that when you like put all of the fuel in your reactor, you've got this fresh fuel that's highly radioactive, and you want that reactor to be critical for like maybe a year before you have to move the fuel around. And so you can put like a poison, like we put boric acid in our reactors, and boron is a neutron poison. So at the beginning, you have like a very high concentration of that boric acid in your coolant to balance out the excess reactivity of your fuel. And then as your fuel fissions and as your fuel burns up, the enrichment slowly decreases. And as that enrichment decreases, you can also lower the amount of boron that you have in your core to make your reactor be critical for like a whole year. Um, and so these are just like some of the pieces that are involved with your real reactors. And today we'll talk more about how we would analyze these configurations when you have like a heterogeneous system. This is a slide that just kind of shows like a detailed picture of a reactor core and all of the different like elements of a reactor core that you want to probably be aware of in nuclear engineering. We've like talked about these before. You've probably seen these before, but oops, just in case you've been hearing any of these terms that you might like want a better definition of, this is pretty standard nomenclature for all of the different like important pieces that you might see in a reactor. Um, and so yeah, that's kind of like that's a good slide just to be aware of and to have it if you're unsure about any of those definitions. Um, in terms of the considerations for like the neutronics of a heterogeneous system, even our fuel is like really a heterogeneous system. Like if you think about in our reactors when we have those little uranium dioxide pellets, If it's a uranium dioxide fuel, that means it's got uranium and it's got oxygen, but then it has different isotopes of uranium because you'll have uranium 235 and uranium 238. So like even those little fuel pellets contain three different kinds of nuclei, which have different cross sections. And what those cross sections do influences how your reactor operates and like how you have to build the reactor to make it operate off of a given kind of fuel. So like this is showing the cross section. So the top right is for uranium 238 and the bottom right is for uranium 235. And then the red plot is your absorption cross section and the blue plot is your fission cross section. So notice that for uranium 238, the absorption is way, way higher than the fission by like 5 or 6 orders of magnitude. So for most neutron energies, it's very unlikely that a uranium 238 can fission unless you get to high energies. Notice that energies like above 1 MeV, these are kind of like right on top of each other, which means that uranium 238 is is fissionable if the neutron energy is high enough, but it's very unlikely to fission if the neutron energy is like below 1 MeV. Whereas for uranium 235, this is a fissile nuclide, which means that it can fission at pretty much any neutron energy. If you look at any given energy here, the fission cross section and the absorption cross section are basically right on top of each other, which means that in terms of like a probability of fission occurring, if you have an absorption in 235, it's very likely to be a fission. And for uranium 235, as the energy of the neutron decreases, the cross section of that reaction increases. So that's why we say uranium 235 is much more easy to fission if you have low energy or thermal neutrons. When you dig uranium out of the, whoops, when you dig uranium out of the earth, natural uranium is about 0.7% U-235 and like 99.3% U-238. So enrichment is the process by which you artificially add uranium-235 to your fuel to increase the percentage of the 235. And that's what we mean when we talk about the enrichment. It's what percentage of U-235 do you have? With U-238, because this absorption is very high, especially in the resonance region, in your nuclear fuel, the U-238 is very good at parasitically absorbing neutrons, and that happens very prominently in like the resonance or like this is the region where you have these resonances that also corresponds to like the slowing down region where neutrons are going from fast to thermal. So the presence of U-238 can act as a neutron capturer or like a parasitic absorber. And that's one of the considerations that we have in our reactor cores is like, how do we get our neutrons to slow down to thermal energies without getting parasitically absorbed in the U-238? Um, and so to get things to slow down, we need a moderator. And that means that within our reactor core, like if it's a thermal reactor and we're trying to make our fissions be off of thermal neutrons, we need fuel and we need moderator so that the neutrons that come out of fission have a moderator that can slow them down to a thermal energy so that when they go back in the fuel, they're more likely to make a new fission happen. So we can talk briefly about like the differences between fast and thermal reactors. In general, reactors use an enrichment of uranium. Typical light water reactors, it's like 3 to 5% U-235. And the exception would be for the CANDU reactor, which is like Canada's flagship nuclear reactor. CANDU stands for Canadian Deuterium Uranium Reactor. They use D2O as a moderator, and that allows them to produce power and be critical using only natural uranium. So that's kind of like a design trade-off with the CANDU, is that enrichment costs money. So if you can use natural uranium, it's a lot cheaper on the fuel side. But then D2O is which is deuterium dioxide. So it's like water, except we've replaced all of the hydrogen with deuterium. And D2O is really expensive. I don't remember like how much it costs like per kilogram, but if you look at like the cost of a CANDU reactor, some like crazy percentage of the cost is just in the heavy water. So design trade-offs there. Um, This top right picture is showing a fuel array for a light water reactor where the circles are the fuel pins. And then in between the fuel pins, you have a region with coolant. That's kind of like the kind of inside of the square here, or in between the circle and the square. That would be like your coolant. And then you have this cladding, or really it's like a structural material for the grid of the assembly where those fuel pins are placed. And so the reason that we kind of have to have things spaced out for a light water reactor means that you have water. And so that would be a thermal reactor because you have a moderator there, which is helping your neutrons go from fast to thermal. And in a thermal reactor, it just means that most of the fissions in your reactor are caused by neutrons that are at thermal energies. And so the whole idea here is that, like, if you think about like this being my fuel, if a neutron in my fuel, if there's a fission in my fuel and a neutron comes out, we want that neutron to be able to like kind of bounce around in this moderating material and slow down to where it gets to thermal energy when it gets to a new fuel element. Because if it can slow down to thermal and then hit a new fuel element, then that thermal neutron is very likely to cause a new fission. And that means that we need to have our fuel more spaced out in a light water reactor or in a thermal reactor so that that moderating material provides space for the neutron to bounce around and slow down before it goes into a new fuel element. Whereas on the bottom right is a kind of fuel loading, typical fuel loading for a fast reactor. In a fast reactor, most of the neutrons are caused by fast neutrons, and that means that you can have your fuel a lot more closely spaced together because you don't need the space between fuel elements to add for moderation if most of your fissions are caused by fast neutrons. Um, and because of needing your fuel more spaced out in a thermal reactor, typically a thermal reactor, like if it's the same power, like 1 megawatt thermal reactor, 1 megawatt fast reactor, typically the thermal reactor is going to end up being larger in volume because we have to kind of be more careful about this fuel to moderator ratio. You want to have enough moderator in your thermal reactor so that neutrons can slow down to thermal energies, but you don't want too much moderator because then you don't have enough fuel to be able to produce power. So generally, fast reactors are like going to be smaller in volume than thermal reactors. And fast reactors are cool too because you can use part of the things that people like fast reactors for is that you can make fast reactors also run on natural uranium because U-238 is able to fission at high neutron energies. So if you have neutrons born at 1 MeV and you don't slow them down, then those fast neutrons are more likely to fission in U-238. You can also make fast reactors run on spent fuel, which is like part of what people like. I think fast reactors are really cool and hopefully going to be more a part of our future, especially if we like get to a point where we start to like run out of uranium 235. Fast reactors are a way that we could make use of all of the spent fuel that we've accumulated. And like the reason spent fuel is dangerous or like radioactive is because partly you have a lot of energy in that fuel that you can still extract if you were to like put it in a fast reactor. So I like fast reactors. I hope we see more of them soon. Um, this picture is giving us some more detail on the heterogeneity of like a reactor core and some of like the really important like pieces of a reactor. So like this is for a typical PWR. This is showing the fuel pellets. Those little cylindrical fuel pellets would be stacked on top of each other. You would surround your fuel pellets with some cladding, which is like a metal kind of sheath that protects the fuel from like leaking out. Like if you were to imagine that fuel having fission events and having fission products coming out of it, you want that cladding surrounding your fuel to be intact so that the fission products stay inside of the cladding. That's why it's a big danger if you have a cladding failure, because it means that fission products can escape your cladding. And if they escape your cladding, that means they're going to get into your coolant. If they get into your coolant, that means that they can make it to other places in your system. So we generally stack our fuel pellets on top of each other. A bunch of fuel pellets stacked on top of each other inside of our cladding makes up a fuel element. And then we take these individual fuel elements and we put them into arrays of fuel assemblies, which would be like collections of like some number by some number of fuel elements, like typically 17 by 17. Within these assemblies, we'll also have other things that aren't fuel, like we might have a control rod, like a hole for control rods. You also have coolant channels so that coolant can flow through these assemblies. Then the heat gets transferred from the fuel to that coolant. If you imagine, this is like a picture of a real reactor core. So you have like the inlet coolant coming in. It enters the bottom of your reactor core and it's passing over these hot fuel elements. In this picture, it's showing that the inlet temperature is 290 Celsius. And as the coolant passes over these fuel elements, heat gets transferred from the fuel to that coolant, which raises the coolant's temperature. So then ends up at an outlet temperature, in this case of like 325 Celsius. And there's lots of other things in our reactor cores that we have, like grid plates are another thing that these fuel assemblies are. You'll have grid plates kind of going vertically up these assemblies. And the point of that is to add, you have like a developing flow. And as that flow develops, when you go from like undeveloped to fully developed, you have less turbulence. And that means that you have like not as good of heat transfer. So we add these spacer grids such that it kind of trips up the boundary layer and allows things to undevelop and get more turbulent, which allows for better mixing and better heat transfer. So lots of these things in our reactors are complicated, but pretty much everything that's in there is there for some kind of reason. And so that's the case of what those grid plates are for. This is just a table of lots of different reactor designs, PWRs, BWRs, high temperature gas reactors, liquid metal fast breeder reactors, gas cooled fast reactors, and the CANDU reactor. And then it's just comparing lots of different information about these different kinds of designs. So this is mostly just like for your information, if you wanted to see like kind of how these things compare against each other. Um, and so when we are talking about a reactor and we're trying to decide, like, do we need to have a detailed treatment of the heterogeneities of the system? Um, We've already talked about the mean free path. And so the mean free path, which we use the symbol X bar, is just 1 over the total cross section. At this point, we want to introduce something called the transport mean free path, which like has the same kind of formula. It's just that the transport mean free path isn't 1 over the total cross section. It's 1 over this thing called the transport cross section. And so the way that we define the transport cross section is that it is the total cross section, and then it's minus this quantity called mu zero bar, and that is multiplied by the scattering cross section. So this is how the transport cross section is defined. It looks just like the total cross section, but then we have this little correction factor, which is this mu zero bar times sigma s. And this thing that we call mu zero bar, that's the average scattering cosine. So when we were talking about last time how different nuclei have a different probability distribution of scattering in a different direction, this is kind of like taking that relationship or taking that information about that scattering distribution and then taking an average of what that scattering angle would be. So it's like the average of that scattering cosine. If you have S-wave scattering, then you can get an analytical expression for this. And this is shown in Dr. Svedkov's notes, but we can just say that it's going to be 2 over 3 times A, where big A is when we defined it last time, we said that it's the mass of the nuclide divided by the mass of the neutron, which ends up being very close to the just atomic mass of the nuclei. So that's why we use the same symbol for atomic mass. And in my class, you can use big A as the atomic mass. But if you're doing like a more detailed reactor design, you probably want to use like the more precise definition. But nevertheless, so notice that U0 bar is always positive. And the scattering cross-section is also always positive. So that means that the transport cross-section is always going to be a little bit less than the total cross-section because it's basically taking the total cross-section and subtracting a little thing off of it. And that means that if I think about the mean free path for the transport mean free path, because the transport cross section is lower, it means that the mean free path for transport is always going to be a little bit higher. Yeah. And so and the reason that we do that is because of we're basically accounting for any anisotropies in the scattering process. What it effectively ends up doing is kind of biasing forward scattering reactions, such that instead of a neutron, it allows for neutrons to go a little bit further before they have their next collision. And so when we talk about a reactor being heterogeneous, we can write down this heterogeneity criterion, which is basically how the mean free paths have to compare to the fuel element dimensions. And what we're going to say is that a reactor can be treated as heterogeneous if the mean free path at some energy E is less than or equal to the characteristic fuel element dimensions. So what we're going to say is that the mean free path, the total mean free path depends on the energy of the neutron, because it's going to be based on cross sections. And that is always going to be less than or equal to the transport mean free path, which is also a function of energy. And a reactor is considered heterogeneous if these transport or the total mean free path are less than or equal to my characteristic fuel element dimensions. And basically what that means, like if I've got a little like circular fuel, well, I guess if you're looking at a cross section of like a fuel pellet, it would be circular. And say the diameter of that fuel element is like 1.5 centimeters. Then if the transport mean free path is less than or equal to that length, then it means that the neutron can have more than one collision while it's inside of the fuel element. And as a result of that, we have to treat that system as heterogeneous. Whereas if the mean free path is a lot bigger than the characteristic fuel element dimensions. Like if the characteristic fuel element dimension is like 1.5 centimeters, but in that reactor, the mean free path is like 20 centimeters, that means it's very unlikely that that neutron would have one collision in that fuel element. And as a result of that, it allows us to simplify the treatment of that system, and we can basically treat it as homogeneous in that case. So this is kind of like just an example to think about how in this context, where like imagine we have some system where the mean free path is 1 centimeter, the transport mean free path is 1.1 centimeters. And remember, the mean free path is just how long, how far a neutron goes before it has a collision on average. So if we have these mean free paths compared to the fuel element or the fuel pin diameter of 1.5 centimeters, then in this case, on average, is the neutron going to have at least one collision while it's inside of that fuel element? It is, right? Because the mean free path is less. So in this case, it would be yes. And if that's true, that means the heterogeneity criterion is satisfied. So we have to treat this reactor as heterogeneous. So we treat the reactor as heterogeneous. And what that basically kind of implies is that if you go from one region to another, like if you go from the fuel to the moderator, the flux can change a lot as you go from the fuel to the moderator because the moderator is slowing the neutrons down. That means that our cross sections are being greatly impacted. And so if you have these like big differences region to region in what your flux is doing, that influences if you have to do a heterogeneous treatment or if you can do something more simple. So in general, for thermal reactors, the mean free path is going to be on the order of like 1 centimeter. And that means that you're going to have mean free paths that are less than your fuel element dimensions. And that means that you have to treat the reactor as heterogeneous. And that kind of makes sense for a thermal reactor because you're going from like fuel to moderator. And the moderator is going to impact my neutrons. It's going to affect their energies, which is going to affect their cross sections. So the flux can change a lot going from like the fuel to the moderator. Compared that to a fast reactor where the mean free path is like on the order of 10 to 50 centimeters, that means that when those neutrons leave that fuel, they aren't being slowed down by like a moderating material. And that means that their mean free path is a lot larger. And it means that you can kind of more simple, you have a way to simplify the way that you look at that kind of design, and you can treat it like more like a homogeneous system. So homogeneous systems are nice because we can simplify the effects of the different materials and like our fuel moderator or fuel coolant, like our fuel lattice. Whereas in a heterogeneous system, you kind of have to treat things in a more detailed way. And so what we're going to do is kind of start talking about the differences between these kinds of systems, how different nuclear properties would change from system to system, and that's going to allow us to have a better decision about when do we treat a reactor as heterogeneous versus homogeneous, and also in those different cases, what kind of analysis would we have to perform? So this is just kind of reminding us about how the cross sections for like a fuel nuclide would depend on energy. And so this is kind of breaking it up into three groups where you've got a fast group, you've got like an intermediate or like a slowing down group or like a resonance group, and then you've got the thermal group. And so notice that in the fast region, that's when our cross section for absorption is the lowest. So if you have fast neutrons in your fuel, it's unlikely that they're going to get absorbed because the absorption cross section is so low. If a if an intermediate energy neutron gets in my fuel, then we have these resonance spikes, which make it very likely that that neutron gets absorbed within that resonance. So if you have intermediate neutrons in your fuel, they are very likely to be parasitically captured by those resonances, and that means that they don't live to cause a new fission. And then in the thermal region, that's where our absorption cross section goes up. Recall that that's also where our fission cross section, like for 235, goes up. So if you get thermal neutrons inside of your fuel, they're pretty easily absorbed and cause a new fission. So that's just kind of reminding us about the differences between those different regions and kind of what's likely to happen to a neutron if it is in those different energy ranges while it's inside of the fuel. So that kind of leads us to a important plot that I want us to be able to sketch. We're going to sketch what the flux distribution looks like for the fast, for the resonance, and for the thermal groups of our reactor. So this is showing an infinite fuel moderator lattice. So the red is the fuel, the blue is the moderator, and then it's infinite. So you would see this like kind of continuing on forever in each direction. I think it would probably be helpful for me to just kind of extend this plot a little bit so that this is like another fuel element, and this is like another fuel element. And then, next to that you would have moderator and it would just go on. It would just go on forever. And so let's try to sketch the fast flux first, and that's our phi1. So if I have fuel and then I have moderator, where do we think the fast flux is going to have a peak? Is the fast flux going to be higher in the fuel or is it going to be higher in the moderator? It's going to be higher in the fuel, right? And why is that? Right, there's nothing to moderate, and also the neutrons get born in the fuel, and when they're born fast. So if we think about like the fast flux, it's going to have like a peak in the fuel, and it's going to kind of just look like a decreasing function as you go towards the moderator. And once you get into the moderator, your fast flux is going to continue to dip. Your fast flux is going to have a minimum in the moderator. So if I were to kind of keep sketching, it's going to have some minimum in the moderator, but then it's an infinite lattice. So it's going to keep going up, and it's going to have this like kind of continuing curve. So this is what our fast flux is going to look like. It's going to peak in the fuel, and it's going to have a minimum in the moderator. That's my phi1. And the reason it has a minimum in the moderator is because once I get into the moderator, then my neutrons are slowing down. So they're like my fast flux decreases in the moderator because that's where neutrons are getting kicked out of that fast energy to go to another energy. The next one that I wanted to sketch was the thermal flux, and I'll do that one in purple. So if the fast flux peaks in the fuel, where do we think the thermal flux is going to peak? In the moderator, right? So I'm going to kind of draw that. It's going to almost be basically the opposite. That my thermal flux is going to peak in the moderator, and it's going to decrease as it gets towards the fuel. And my fuel, my thermal flux is going to have a minimum. And the reason that my thermal flux has a minimum in the fuel is because when my thermal neutrons go into the fuel, they cause fissions and they make new fast neutrons. And then it's an infinite lattice, so this is going to kind of continue like so. So the fast and the thermal flux kind of do the opposite thing. And then the resonance one is a little bit more tricky. Um, so the resonance. What we can say generally is that the moderator isn't going to really do that much to resonance neutrons in that, like, when what the moderator is going to do is just slow my neutrons down. So it's not really going to like, there's not really going to be that much regional variation in my resonance flux in the moderator. In the moderator, it's basically going to be more or less like kind of like a constant. And if my resonance neutrons get into the fuel, in the fuel we have these big resonance absorption spikes. And so when the resonance flux gets into the fuel, it very quickly diminishes. So that's what these like kind of lines going down are showing. It's showing that it's like basically going to zero. The flux like basically goes to zero when the resonance neutrons get into the fuel. That those absorption cross sections for the resonance region in my fuel are very high. Any intermediate energy neutrons that make it back into the fuel are probably just going to get captured by uranium 238. And that means that they're gone from our system and they can't cause any new fissions. So if you think about what's happening with this resonance flux, it's almost like the fuel is like shielding the inner parts of itself from those intermediate neutrons. Like the middle part of my fuel, the intermediate flux doesn't really make it there. So the fact that my fuel kind of eats up all those resonance neutrons before they even make it far into the fuel, that's an example of what we would call spatial self-shielding. That's an example of spatial self-shield. So with that being said, this is a good plot to be familiar with. I might ask you to sketch this plot later on. So if you don't understand that plot, try to ask questions if there's anything we're confused about. And if not, that might be something that I would ask you to reproduce. Oh yeah, and sorry, I forgot to label it, but that was my phi 2. That was my intermediate flux. Yes. Yeah, so basically what we're saying about the intermediate flux is that it doesn't really have that much variation in the moderator. Essentially, what the intermediate flux is, we're kind of imagining that these thermal neutrons are slowing down, they're becoming intermediate, and then they're continue to sorry, I have this backwards. The fast neutrons are slowing down, becoming intermediate. Those intermediate neutrons are continuing to slow down to become thermal. And then once if these intermediate neutrons were to make their way into the fuel is going to quickly capture them because of that resonance absorption region right here. And so they kind of get eaten up before they even make it anywhere else into the fuel. So the next thing I wanted us to do is kind of review slash reintroduce the 4 and the 6 factor formulas for the multiplication factor. And we want to remember how to do this so that we can then talk about how would these terms that appear in our 4 and 6 factor formula change if we had a heterogeneous configuration versus a homogeneous configuration. So we kind of have to introduce some terms to be able to put all of this together. All of these terms are basically just probabilities of different things happening as we track the neutron life cycle from when they're born fast to all the different things that they do in our reactor as they go through the reactor. So we're going to introduce P, F, and L, which is the fast non-leakage probability. So that the P is a probability, the F and L is fast non-leakage. And this is the probability that a fast neutron doesn't leak. Fast non-leakage means that it's just the probability that a fast neutron doesn't. The PTNL, and if you downloaded these slides like earlier in the day, this might be an F because I had a typo. Make sure that you change, or sorry, no, this might say fast. I had a little typo. Make sure that this PTNL stands for the thermal non-leakage probability, and that is a similar thing. It's a probability to that a thermal neutron doesn't leak. We use a little p for this resonance escape probability. That kind of, as the name implies, relates to a fast neutron not being absorbed while it's slowing down to thermal, um, given that it doesn't leak. So given that it doesn't leak, I can fix that K because it looks really bad. Given that it doesn't leak. So like, yeah, those fast neutrons, if they become intermediate while they're slowing down to thermal, they might get absorbed in my fuel. This is the probability that they don't get absorbed as they make their way from fast to thermal. Little f is the thermal utilization, which is the probability that a thermal neutron is absorbed in fuel, given that it was absorbed while it was thermal. Given that it was absorbed while thermal. We use a U with the subscript F to denote the fast utilization. That is the probability that a fast neutron is absorbed in the fuel, given that it was absorbed while fast. And those two will make more sense when we draw the probability tree, because we'll have a fast branch and we'll have a thermal branch. Um, and then PTAF is a probability that a thermal absorption results in a fission. So thermal absorption causes fission is what those kind of letters are telling me about. The PFAF is the probability that a fast neutron has an absorption that causes a fission. And then we introduce, oh, this is kind of in the way, huh? Oh, that's cool. These are news. So that's a nu with a subscript T. That's a nu with a subscript F. It tells me about the average number of neutrons that are coming out of either thermal fissions or fast fissions. So with all of these little probabilities, we can use those definitions to track the neutron life cycle, to see kind of what neutrons do when they start out. And when they start out, fast neutrons come into being because they get born from fission. And when a fast neutron's born, it kind of has two possible outcomes. And that's what these different arrows are showing. And so if a fast neutron gets born from fission, the first kind of thing that can happen is that fast neutron can end up leaking out of our system, or it might not leak. So over here, I'm going to show that's what happens if it leaks. And then right here is going to be if it doesn't leak. If we have a fast neutron that doesn't leak, what's the probability that a fast neutron doesn't leak? Yeah, the PFNL, right? PFNL, perfect. And so if this is like a probability branch, and so there's only two outcomes. It's either leaks or doesn't leak. And if we know that the probability that it doesn't leak is sorry, is PFNL, like if this probability was 75%, then what's the probability that it leaks? Yeah, it would be 25% or 1 minus PFNL. So this is going to be 1 minus PFNL. And then we can kind of play this game as we go through the tree. So once that fast neutron is in our system and we know it's not going to leak, then the next thing that it can happen is it's still fast. So one thing that can happen is that it gets absorbed while it's fast. And so that's what I'm going to show on the right. This is absorbed while fast. The other thing that that fast neutron could do is it could have a bunch of scattering reactions that slow it down to thermal. So that's what is going to be on the left. It's going to be slows to thermal. If a fast neutron doesn't leak and it slows to thermal, that probability was the it's a resonance escape probability because it's slowing down to thermal without getting absorbed in one of those resonances. So that's my resonance escape probability. And if that's my resonance escape probability and I only have two other options, then this right here is one minus the resonance escape probability. And so this kind of we had the neutrons that were born fast and then they separated into two different branches. And this branch corresponds to slowing to thermal. So we're going to call this the thermal branch. And then obviously going this way is going to be my fast branch. Two different branches of this probability tree. And so I'm just going to kind of go along the fast route. Um, if we are absorbed while fast, we could be absorbed into two different things. We could be absorbed into fuel, which is nice because that could cause a new fission. So this is going to be absorbed in fuel. But there's other stuff in our reactor. Like there might be structural steel, there might be even the moderator. You could still be absorbed into something that doesn't cause a new fission, in which case the probability tree dies. So I'm just going to say on this other branch, I'm going to say absorbed in junk. And junk is just anything in my reactor that's not fuel. And kind of like when I was right here and I showed that neutron leaking, I didn't draw any branches after that because once the neutron leaks, it's dead. I don't care about what happens to it anymore because it can't cause any new fissions after that. And same thing if that neutron gets absorbed in junk. That probability tree also dies right there because if it's absorbed in junk, then it can't have any new children neutrons, so that part of the probability tree dies. And then if we get absorbed into fuel, there's two more options. We can be absorbed into fuel and not fission, or we can be absorbed into fuel and fission. So this is going to be the branch that dies. So this is going to be doesn't fission. And then this is going to be absorbed in fuel and fissions. So this is going to be causes fission. And if we were absorbed while fast and we were absorbed in the fuel, that's the U sub F. That was my fast utilization, probability that a fast neutron is absorbed in fuel given that it was absorbed while fast. So that's my fast utilization right here. Technically, this would be 1 minus UF, but that part of the probability tree is going to die, so we don't really need to write it. Um, and then if we're absorbed in fuel and we cause a fission, that was the PFAF. And this fast neutron that causes a fission is going to produce new fission neutrons. So this little arrow is going to be new fast. And these fast fission neutrons kind of recreate the probability tree. And they cause a new generation of fast neutrons to be born, which could then go through the same process. So that's like what the fast branch looks like. And then we have the thermal branch that we want to talk about too. So we kind of stopped with them slowing to thermal. If a neutron slows to thermal, it kind of has two options. That thermal neutron could leak or it could get absorbed. So this is going to be leaks, and this is going to be absorbed. If a neutron slows to thermal and gets absorbed, what probability does that correspond to? Yeah, PTNL, right? PTNL, the thermal non-leakage probability. And so, yeah, just like what you're saying before, if that thermal neutron leaks, that probability tree is dead. So we don't really care about it. Technically, this branch would be 1 minus PTNL, but it's not going to end up in our final result because that part of the tree died. Um, and then once that thermal neutron gets absorbed, it could be absorbed into two things. It could be absorbed into junk, in which case the probability tree dies, or it could be absorbed in fuel. And if a thermal neutron gets absorbed and it gets absorbed in the fuel, then that probability was F. And if we get absorbed into the fuel, then we can do two things. We could cause a fission, in which case we make new neutrons. Or we could be absorbed into something that doesn't make a fission. We might just get captured into like the uranium-238. And if we get absorbed in the fuel while we're thermal and we cause a fission, that was the PTAF. And that thermal neutron that causes fission, it's going to produce new fission neutrons, and that would be the eta thermal. So and those neutrons born from a thermal fission, they're still going to be born fast. They're going to make it back to the beginning of this probability tree. And that, so essentially, as you go through, this is showing the neutron life cycle. It's showing how a fast neutron could make new neutrons, and those new neutrons can then come back and repeat the cycle. And ideally, we set up our reactor such that the number of neutrons that are getting born from fission exactly balance the number of neutrons that are getting lost through these different parts of the probability tree that are dying, such that our reactor is critical and that the number of neutrons born in one generation equals the number that were produced in the next generation. And so that's another way that you can think about K effective is based on like balancing production and loss mechanisms. You could also thinking about the population of your neutrons in one generation compared to the population in the next generation. And so in principle, what we could do is take all of these different parts. So like if we look at the probability, if we look at the branches that survive, if we just kind of make notes of which way we went to actually make a new neutron come out, if we multiply all of these probabilities together, that'll give us an overall probability that a fast neutron born from fission becomes thermal, gets absorbed into fuel, causes a fission, and produces new neutrons. So if we multiply all those together, that would be part of our like multiplication factor. And if we would also want to track the fast branch, which would be going this way. And if we multiply all of those probabilities together, those would add up to give me the number of neutrons that are coming out of the fast branch. So in practice, what we do next is we just follow the surviving parts of that probability distribution, multiply all those probabilities together, and then we've got two branches, so we're going to like add those two parts up. So from that, that's how we can get a definition for K effective based on all of these probabilities. So like both of them started with P, F, and L. And then we kind of had those two different parts of the branch. The first was I'll show the thermal branch first. So we had the resonance escape probability. We had P, T, N, L. We had that thermal utilization factor. We had P, T, A, F. And then we had eta thermal. Those were all of the probabilities that I would multiply together to make up my thermal branch. And then the next term is going to be based on my fast branch. We had a P, F, N, L up front, and then we had 1 minus P. We had the fast utilization factor. We had P, F, A, F. And then we had eta fast. And one thing that we can do is we can lump some of these terms together. So the PTAF and the nu T, this was like the probability that a thermal absorption results in fission. And this was the number of neutrons that come out of that thermal fission. We can take those together and create something called eta thermal, which is basically the number of thermal neutrons produced per thermal absorption. And we could also lump the PFAF and the nu F together to give us an eta fast, which is the number of fast neutrons produced per fast absorption. And um, because this K effective formula has these two terms basically, it's customary to define this thing called epsilon, and epsilon is called the fast fission factor. This is the fast fission factor. Um, by definition, it's the total number of neutrons coming out of all fissions divided by the number of neutrons coming out just from thermal fissions. And then that can simplify to give me something that looks like this. And we can then take this definition and plug it into our definition for K effective to turn it into something that has two terms and make something that just has one term. So if I substitute in the fast fission factor, then that gives us the famous six-factor formula for the multiplication factor, which looks like P F N L times the resonance escape probability P times P T N L times the thermal utilization times that eta thermal and times that fast fission factor epsilon. So that right there is the famous six-factor formula for K effective. Notice it's got 1, 2, 3, 4, 5, 6 terms that are all relating to different probabilities of different things happening as my neutrons go through their life cycle. So in principle, if you knew what all of these probabilities were, like if you could get expressions for them, then you could determine K effective just by multiplying those probabilities together. Um, we can also take this. So this was the effective multiplication factor, which included the possibility that neutrons leaked out of our system. If we have an infinite medium, then there's no leakage, and we can kind of simplify this formula and get a four-factor formula for K infinity. Which of these probabilities related to leakage? The TNL and also the FNL, right? And so if there's no leakage, what would be the PFNL and the PTNL equal to? They'd be equal to 1, right? Because that's the probability that a fast neutron doesn't leak, and that's the probability that a thermal neutron doesn't leak. And if there's no leakage, then the probability that it doesn't leak is 100%. So both of those become 1, and then those two terms basically drop out of the equation. So the four-factor formula is just little p times F times eta thermal times epsilon. So that's my famous four-factor formula. And then this was my famous six-factor formula. And so it's good to remember how that came about, and it's good to kind of refresh ourselves on these different probabilities, because then we can start thinking about how these probabilities would be impacted by if we had a heterogeneous kind of approach to our reactor system, or if we had a homogeneous approach to our reactor system. So like, oh, when we were doing section 4, we came up with that two-group diffusion model. And on the exam, you had a question about deriving the effective multiplication factor for that two-group model. If you were to construct all of these different probabilities, then you could take your you could express these probabilities in the context of two-group diffusion, and then you could multiply them all together, and you would get something that looks just like what you should have gotten for that effective multiplication factor for that problem. And the derivations to show how you can create all of these from the two-group diffusion model are shown in section 4.2 of Dr. Svedkov's notes. So that's just something to be aware of. And what I wanted to do next was start talking about how those four-factor terms would vary in certain contexts. So this is showing how F and P and epsilon vary for a system that has a different amount of fuel to moderator in my system. So like here on the x-axis, x represents the number of uranium atoms per the number of H2O molecules. So zero means I have zero fuel. And then as I go to the right, I'm increasing the number of uranium atoms that I have per H2O molecule. So I get one, that would mean one uranium per number of H2O atoms. If I got all the way to 3.2, that means I have 3.2 uranium atoms for every H2O molecule. And so if we talk about F, which is that thermal utilization factor, then notice that F, when X is zero, F is zero. Because if I have no fuel, then I have no thermal absorptions in the fuel. And as I increase X, which means I'm increasing the amount of fuel in my system, notice that F increases. And as I continue to increase X, F gets closer and closer to 1. So I think that one probably makes sense in that if you have more fuel, then you get more thermal absorptions, and that means that the thermal utilization factor goes up. P, the resonance escape probability, when X is 0, P is 1. And and remember, P is the number of neutrons that slow to thermal while they're being absorbed. So if X is 0, that means all that I have is moderator. And if my whole system is just moderator, then any neutron that's bouncing around in that moderator has a 100% chance of slowing down to thermal because it basically can't do anything else. And then as I increase the amount of fuel in my system, that that resonance escape probability goes down because if there's more fuel, that means that there's more material that could parasitically absorb the neutrons as they were slowing from fast to thermal. Like if I'm fast and I'm in the moderator and then I slow down to an intermediate energy and then I go in the fuel, then I'm going to get absorbed by that fuel. So as the fuel amount increases, the probability of getting captured in that fuel in the resonance region increase. That probability, the resonance escape probability, ends up decreasing. And then epsilon is the fast fission factor. You can think of it as 1 plus the number of fast fission neutrons divided by the number of thermal fission neutrons. And it also starts at 1 because if there's no fuel, then that means that there's basically no fissions at all happening. So this whole term kind of drops away. And then as I increase X, epsilon increases too. And that's because as I add fuel, then I'm both increasing the amount of fuel and I'm decreasing the amount of moderator. So with less moderation, I get less thermal neutrons. And that means that the number of thermal fission neutrons goes down. And as a result of this part of my fraction going down, this overall term goes up. So the 1 plus this becomes bigger and bigger, and then my epsilon increases as X increases. And K infinity is epsilon times F times P, also times the eta F. But eta is a little bit more complicated, so we kind of talk about eta later. But if I think about these three probabilities being related to K infinity, notice that epsilon and F go up as P goes down. So at some point, there's a maximum based on these two increasing and P decreasing, as a result of the fact that some of these are increasing and some of these are decreasing, it means that I get 2 points where my K infinity would be equal to 1. There's one value where K infinity is equal to 1 at a relatively low value of X, like 0.07. And then there's this other value of K infinity equals 1 where X is about 2.5. And according to this, the K infinity has a maximum at this X value, which corresponds to a K infinity of about 1.27. And so in general, K infinity can be greater than 1. And in general, for a fuel, you want your K infinity to be like as large as possible, because then once you make a real reactor, you get some leakage, which means your K effective goes down. And you want your K to be kind of as high as possible, because that is going to allow your reactor to stay critical for longer. Because even if your K for your fuel is like greater than one, you can do things in your system to kind of balance that out so that you can remain at K equals one for the entire system over like a longer period of time. This is another plot that is kind of similar, but it's just showing how K effective gets impacted by different moderators and different fuel volume fractions. So this plot is for a spherical reflected reactor where the total reactor has a radius of 1 meter. And here x is the fuel volume fraction. So x equals 0 means I have no fuel and it's just a single moderating sphere. X a fuel volume fraction of 1 means I just have a giant sphere of fuel and no moderator. And in between, it means that I have a fuel region surrounded by a moderating region. And this one is really interesting because notice that like if I start with all fuel and then I decrease the amount of fuel and therefore increase the amount of moderator, all of these types of moderators down here, beryllium, beryllium oxide, and graphite, in decreasing the amount of fuel results in these K effectives going down. Whereas if my moderator contains hydrogen, like H2O or zirconium, these different kinds of zirconium, zirconium hydride or yttrium hydride, something really interesting happens, which is that as I decrease the amount of fuel, my K infinity, my K effective actually starts to go up. And that kind of speaks to the moderating effectiveness of moderators that contain hydrogen. And it happens as a kind of consequence of both the moderating ability of hydrogen, but also it kind of relates to the fact that this is a small reactor where you have to be more spatially conscious about how much moderating material you need to achieve a critical system. And so the thing about like graphite and beryllium is that like if you look at graphite, it has a good moderating power, but the mean free path in graphite is very, very large, which means that if you want to make a reactor critical with graphite, you need a lot of graphite to get the effect that you want, meaning that ideally graphite is going to slow your neutrons down, make them thermal so that they can cause a new thermal fission. But as you increase the amount of moderator in your system, the K effective for a graphite moderated system just continues to go down because all you're doing is replacing fuel with moderator. And by the time that you've added enough moderator to get the moderating ability that you want out of graphite, you've used up so much fuel that you don't really make any fissions happen. Whereas with hydrogen, it has a good moderating power and a good moderating ratio. And the mean free path for hydrogen is really small. So you only need like a little bit of water to get the effect that you want. And that is kind of those things working together is what allows you to actually get an optimum K effective by reducing the amount of fuel that you have if you're using the right moderator. And this was for like a small, like a micro reactor. So it kind of speaks to needing different kinds of moderators for different kinds of designs. If space conservation is the thing that you're most concerned about, you need a really, really good moderator that's very spatially efficient. And so that would mean like hydrogen bearing moderators versus if you don't really care about the size, then you can get away with using like a graphite moderator. And this is also kind of why if you compare graphite moderators to water moderated reactors, the graphite moderated reactors end up being much larger because you just need more space to get the effect out of carbon that you need. So this is starting to get us into thinking about what is a heterogeneous system versus what is a homogeneous system. Because if we can understand the difference between those two configurations, then we can better understand in which case would these probabilities in my 6 and 4 factor formula be like larger or smaller. So in a heterogeneous configuration, you have distinct regions where everything is just one kind of material. So like this is showing like a lattice of fuel elements surrounded by their cladding, and then the blue is like the moderator around those fuel elements. And so you have very different properties if you were comparing the fuel to the cladding to the moderator, and you get the full effect of those different materials depending on whatever region your neutrons are in. So this is what a heterogeneous configuration looks like, where you have these distinct regions with very different material properties going from region to region. If we think about a homogeneous configuration, it means that we're taking this complicated thing and we're like throwing it in a blender where it all kind of smudges out or averages the properties of all of the different things that are coming together. So that if I were to look at like any piece of this system, within this little piece, it's going to contain everything that I have. This little piece is going to contain fuel, it's going to contain clad, and it's going to contain moderator. And anywhere I looked in my system, it's going to be the same. I'm getting like kind of all of the effects of all these different materials everywhere that I look. It's like everything is very uniform and kind of averaged. All of the different regional variations in my properties get kind of averaged out in the homogeneous configuration, whereas they're distinct and they have more of their individual impacts in the heterogeneous configuration. So, um, based on kind of that discussion about what does a heterogeneous versus a homogeneous configuration look like, we can start thinking about those different terms in our four and our six factor formula. And we can start thinking about in which context, heterogeneous versus homogeneous, would those probabilities be larger or smaller? So if I think about P as the resonance escape probability, which relates to the fraction of fission neutrons that can slow from fast to thermal without being absorbed, we want to think about the fact that for something to go from fast to thermal, it has to make it through that intermediate range, and it has to not be absorbed while it's in that intermediate range. So we need good moderation to escape those resonances so that our neutrons can get to a thermal energy and not get absorbed while they're in the fuel. So if I think about the heterogeneous configuration versus the homogeneous configuration, which one is going to allow for better moderation? Yeah, the heterogeneous one, right? The heterogeneous, absolutely. Hetero, uh, Heterogeneous is going to allow for more moderation because if I'm a neutron that's born in the fuel and then I make it into the moderator, I only see moderator for a decent amount of space, and therefore I can bounce around quite a bit, slow down to thermal energies before I make it back in the fuel. Whereas if I'm in the homogeneous system, if I'm born from fission somewhere, then I immediately start seeing moderator and I end up seeing fuel kind of at the same time. And so I might get moderated a little bit, but then I'm also seeing fuel, which would allow me to more easily get absorbed in a resonance. So therefore, if I think about the resonance escape probability, P for the heterogeneous system is going to be larger than P for the homogeneous system as a consequence of getting better moderation and being able to slow down to thermal before I um, see a fuel element, which would get me absorbed maybe if I was still intermediate and I saw that fuel instead. Awesome. The next one would be the thermal utilization factor. We can think of the thermal utilization factor as just the number of neutrons absorbed in the fuel divided by the total number of neutrons absorbed. And for this one, we kind of want to think about what happens if I get absorbed in fuel, and in which cases is it more likely to be for me to see fuel versus um, to see something else. So like if I have a heterogeneous system, then my fuel is kind of like this distinct region and it has spatial variation. So like I can almost imagine like we have that spatial self-shielding effect where if I were to imagine a neutron being born from fission and bouncing around, when I get back into this fuel element, I kind of have like a big layer of fuel that's stopping me from seeing the fuel that's like closer into the fuel element. And so that means that in the heterogeneous system, I have spatial self-shielding, which kind of stops some of my fuel from really seeing as many neutrons because the outer part of my fuel is going to block them. Whereas in a homogeneous system, I kind of see fuel everywhere where I'm at. So if I think about the fact of spatial self-shielding, in the heterogeneous case, I actually have less absorption in the fuel than I would in the homogeneous case. So if in the heterogeneous case, because of self-shielding, I have less absorption in the fuel because some of my fuel just gets self-shielded. And if I get less absorption in the fuel in the heterogeneous case, then that means that I have a lower thermal utilization in the heterogeneous case. So that means that the F for my homogeneous case is going to be bigger than my F for the heterogeneous case. Less in the homogeneous case, there's less spatial self-shielding, so there's kind of fuel everywhere, so neutrons more likely to be absorbed in fuel because anytime that there is fuel, it's kind of it doesn't have fuel around it to stop it from being self-shielded. So that's what we can say about the thermal utilization factor. And then the last one we want to talk about is the fast fission factor. And for a heterogeneous system, we have to be careful about how we define the fast fission factor because the fast fission factor depends on the resonance escape probability. And therefore, we need to pick a definition that's like consistent with both of them. So if we define some energy E0, that's an energy that we can maybe say about 1 keV, where below that energy, fast neutrons basically, neutrons aren't born from fission. Because most neutrons are born fast. So if we set our cutoff at like 1 keV, we can pretty safely say below that E0 that neutrons aren't being born from fission in that range. So if we have a neutron in that energy range below E0, that means that the way that it got there was by first scattering and slowing down with the moderator to get to that energy below where the neutrons wouldn't be born from fission at that energy. If they get to that energy, it's because they got there by slowing down in the moderator. So if we're only able to get to those lower energies by slowing down in the moderator, then we can kind of redefine the fast fission factor in this context to talk about the number of neutrons that slow down below that energy divided by the neutrons that come out of thermal fissions. And then if we want to talk about which one is going to be larger, the heterogeneous case versus the homogeneous case, we kind of just need to ask the question again, in which one do we have better moderation? Because if we have better moderation, that means that we can slow down below that cutoff. And then that means that the fast fission factor would be higher in the case that has more moderation. And we kind of already said that the one that had more moderation was the heterogeneous system. So that means that the epsilon for the heterogeneous system is going to be bigger than the epsilon for the homogeneous system. So that's how those three terms in the four-factor formula would vary from configuration to configuration. We kind of haven't talked about eta because eta is kind of a more complicated thing that you would need to know what your flux distribution is to be able to talk about eta. But what we had just said is that for the homogeneous case, the thermal utilization is highest. And then for the resonance escape probability and the fast fission factor, the heterogeneous configuration is going to be higher. So we kind of have like a balance of these competing factors if we think about in which case is K infinity going to be larger or smaller, because it kind of depends on if the P and the epsilon, if their gains are offset by the losses in the thermal utilization factor. And as it turns out, which one is bigger or larger, or which one where the offsets kind of overpower each other, depends on the enrichment of the fuel. And so if we use omega to be the symbol for the U-235 enrichment in like an atom percent, then all of this above is going to be true. And really what we're saying is that the offset in F is going to be that the offset in P and E is going to overpower the decrease in F. That's going to be true if the enrichment is about less than 5%. So if we say that omega, which is the percent 235 enrichment, and when I say percent, it's like an atom percent. If this omega is less than or equal to 5%, then the gains of these guys overpowers the losses of this guy. And that means that the K infinity for the heterogeneous case would be larger than the K infinity for the homogeneous case. And then if the enrichment is greater than 5%, then the increase in F overpowers the increases in P and epsilon. So if omega is greater than 5%, then it's the opposite is true. And then K infinity for the homogeneous case would be bigger than K infinity for the heterogeneous case. So that kind of helps us understand in which contexts is my infinite multiplication factor going to be larger. It kind of depends on my enrichment. Um, and so that just helps us kind of better see some of the different contexts in which we can consider a system to be heterogeneous versus homogeneous. What would be the implications of a system having that kind of treatment of heterogeneous versus homogeneous? And if that's okay, then we can talk a little bit more about like what would it mean to deal with a real reactor. And if you think about a real reactor, this giant system with lots of different moving pieces, like if you think about just the number of fuel elements in a reactor, usually reactors have about 200 fuel assemblies, and then each of those assemblies is a 17 by 17 array of fuel elements. So that means like about 58,000 total elements. About 55,000 of those would just be fuel. So you have a bunch of fuel in your system, all in these different locations, and then you have different kind of things going on around that fuel. So you have multiple regions. The physics that's involved with describing that system depends on the energy of the neutrons. So if you wanted to model a big reactor like this, you need multi-group, multi-region diffusion, and then you need to be able to solve that equation at like a bunch of different points within that system. If you think about breaking that system up into a bunch of little like control elements or control volumes that you would solve over, then you would need like millions of those mesh elements where you're solving those multi-group, multi-diffusion equations in each of those regions to like accurately model a system like this. And doing all of that is only going to give you neutronics information. Like it's only going to tell you about what the flux is doing, and what like your power distribution is. But you would need to do more analysis to actually design a core. Like if you know what your flux and power distribution is, that doesn't really tell you about what your coolant is doing. Like it doesn't tell you about the temperature gradient through your system. You would need and temperature distribution through your system. You would need to be able to do heat transfer and like CFD calculations for understanding those other elements of the system. So it's like there's lots of different, like if you're trying to be involved in nuclear engineering, there's lots of different paths you could take. You could be like a neutronics person that like only focuses on like neutron diffusion. You could be like a CFD, kind of like a mechanical engineer person where you focus more on like the heat transfer and the fluid flow. You could do nuclear thermal hydraulics and then you get to do both. And so, yeah, there's a lot that goes on with these things. If you are trying to decide what you want to do, it kind of depends on what your problem is and like how deep you need to go. Like what's the purpose of your analysis? Is it a homework? In which case you could probably do much more simplified things. Is it like your senior design or is it a job, which would be like kind of increasing complexity for your problem? And then also what kind of reactor you're trying to work with will influence other aspects of the complexity. And in general, what we're trying to do is do something that's computationally efficient so that it doesn't take us like a million years to run our system, to run our model, but also something that's accurate enough to be able to give us good predictions. And so The heterogeneity treatment is kind of gonna help us in context where we need to do it. But that also means that we need to know stuff about our flux distribution so that we can do the calculations that we need to do. And in general, the kind of approaches that you have are either analytical approaches, which is like mostly what we focus on in this class, but there's also Monte Carlo, like statistical approaches, which use like generating random numbers and running through lots and lots of possibilities to determine similar kinds of results. The reason that people like Monte Carlo is because as your problem gets more complicated, the amount of time that it takes to get a decent solution ends up being less than if you have to like do analytical or deterministic neutron diffusion or neutron transport calculations, especially for like a giant reactor. Um, so Um, in terms of talking more about like what would it mean to take this heterogeneous process and homogenize it, what we're basically saying here is that like this is kind of what a real reactor core would look like, where each of these little squares is an assembly within my core, and you have different enrichments in different regions of your real reactor core so that you can have a more like balanced uniform flux profile. And what we're going to do first is just kind of simplify this very detailed reactor core and simplify it as an infinite array of fuel and moderator cells. So that's kind of what this picture is showing. And what we're saying, what we're going to assume as a part of this is that the number of cells in my system is going to be equal to the volume of the core, the entire volume of this reactor core divided by the volume of a single cell. Um, so that's just kind of like that's how we can describe how many individual cells that we have. And when we say the number of cells, that would be like a single fuel moderator cell. And so if I were to have some infinite configuration like this, and I looked at any individual piece of my system, I could break it up into a bunch of these cells. And if I were to determine the volume of a cell, and then I took the volume of that cell, did the volume of the core divided by the volume of the cell, that would give me some idea about the number of cells that I was dealing with. When we say infinite, it's not really an infinite number of cells. We're just kind of using infinite to say that like if I look from one cell to another, if it's an infinite lattice, then whatever like distribution I have around one cell is going to be equal to the distribution I would see around any other cell. So that's kind of like the advantage of replacing this complicated reactor core with this infinite moderator, fuel moderator, infinite array of fuel and moderator cells. And so what we're saying is that if you in this assumption about it being an infinite array of cells, the convenience of that is that each individual cell is going to be identical to another in terms of what the temperature profile, what the flux profile around any individual cell looks like. And that was kind of like what I was showing on the previous page where I was drawing out a cell. This would be like one of those cells. And if we wanted to do our calculations just on a cell basis, then what we could do, the simplest thing that we could do is just volumetrically average the cross sections in each region to the volume fraction of those parts of my cell. Like in this case, my cell has fuel, has cladding, and has moderator. So the way that I could get like a cell average cross section is I would take like the cross section for whatever reaction type X for my fuel. And then I could multiply that by the volume of my fuel to the volume of my cell. And then, so that's taking the cell cross section, the fuel cross section and multiplying by that fuel volume fraction. And this is what I would call simple volumetric averaging. And I would do the same thing for the other materials in my system. So like the cross section for the clad would be a part of this, and I would multiply that by the volume of my clad to the volume of my cell. And also I would do this for my moderator. My cross section for the moderator would be there, and it would be multiplied by the volume of my moderator divided by the volume of my cell. So this is simple volumetric averaging of my cross sections. I'm not just adding up the individual cross sections, I'm also adding this multiplier that kind of accounts for how much of my fuel do I have relative to everything else. Because if you just added the cross sections together, you wouldn't be accounting for the fact that, like, what if my fuel takes up almost all of the cell? Then my cross section is going to look a lot more just like the fuel cross section versus if I have like equal parts fuel, moderator, or different parts, then adding these volume fractions kind of helps in the averaging process. But either way, this is just a cross section that represents the type X cross section. Also, this could be for some group. I forgot to put the subscript G, but technically you could do this for lots of different groups of energies within your system. And X could just be any kind of cross section. Like if it's a cell average fission cross section, then X would be for fission or capture or absorption or whatever cell average property I want. In the end of the day, these are all just cross sections which have the same units of the number of reactions per neutron distance travel. So this approach might look okay, but part of the reason that this approach fails, or it can fail, is that we're not accounting for something really important. And what we're not accounting for is the fact that the flux also varies from region to region. So we're not accounting for regional variations in my flux. And that flux is going to depend on where I am and on the energy of my neutrons. So like if I'm in the fuel versus the moderator, my flux is going to change. It's going to change quite a bit. So the way that I handle that is I add something called a flux disadvantage factor, where we use this funny Greek letter zeta for the flux disadvantage factor. And that flux disadvantage factor for a given cell says take the flux for that group in that region and divide it by the flux for that group for the entire cell. And I is just an index that represents like whatever my materials are. So like using that previous example, you would have a value for the fuel, you would have a value for the moderator, and you would have a value for the cladding. So the more appropriate way to average my cross sections is to do a combination of volumetric averaging and flux disadvantage factor averaging so that I'm accounting for not only how much material do I have in that region compared to the total, but also how does the flux in that region compare to the total? Because the value of my flux is gonna relate to how heavily I weight that cross section for that material. So this is the most proper way that we could average cells. Um, but and if we had this, then we could do multi-group diffusion instead of having to do it for multiple regions. We could just have like a cell averaged homogeneous kind of system that we look at. So if we had all this, then we could do multi-group diffusion, just like we had been doing before. And that would give us information about the flux distribution in some particular unit cell. Um, the problem with this approach, though, is that if I want to do diffusion, I'm usually solving for the flux, but this approach requires that I know the flux to get my flux disadvantage factors. So the issue is that we need the flux to compute my my flux disadvantage factor. Um, and so we have to know when we can ignore flux disadvantage factors and when we cannot. This is my definition of the flux disadvantage factor. And so when I have big variations in my flux from region to region, I can't ignore the flux disadvantage factors. And that's going to happen in a thermal reactor. Because in the thermal reactor, if I go from like the fuel to the moderator, there's going to be a big change in my flux. And therefore, these disadvantage factors is something that I can't ignore. So these are not something I can ignore if it's a thermal reactor. But if it's a fast reactor, then there's not going to be that much difference in my flux from region to region. And that means that the flux in my fuel and my moderator and then my coolant is going to be very similar to the overall flux. And that means that these flux disadvantage factors are basically one. And so then if each of those flux disadvantage factors is basically one, then I can get away with just simple volumetric averaging, and I don't need to include anything about my my flux disadvantage factors. And so that ends up being really important because when we do our project, the reactor design project, it's going to be for a fast reactor. And that means that we can ignore our flux disadvantage factors when we homogenize our cross sections. So I'll release the reactor design problem. Now that we've seen this, I think when we come back on Wednesday, I'll release the reactor design problem so that you guys have a good amount of time to work on it. And I'll also talk a little bit more about the reactor design problem itself, kind of give you guys a good starting point for how you would want to approach that problem. So yeah, that's everything that we wanted to say about chapter 5. That also should give you everything that you need to do the problem set number 4. If you have any questions about that or questions about anything else, let me know, and we'll talk more about that reactor design problem next time. Also, I'm almost done with your exams. I have like just a couple more, like the last 2 problems